Okay, so take two. Today is the session on the design of 3D printer extruders. So the perspective on that is that there's two main items on our side, is the ability to print with rubber, which is thermoplastic elastomer. Rubber is printable on 3D printers, and for our applications this is about rubber O-rings up to tractor tires. Very important parts of the modern economy. For the issue of accessibility to such extruders is that they do not exist. There is no optimized 3mm printing extruder, and then 3mm is the standard large filament, and we also want to go larger for printing larger and faster. So currently we have the ability to buy a $250 extruder, the Super Volcano, with a Super Volcano nozzle, which allows us to print about 20 pounds per day of plastic. So that's the industry standard state of art that can be done with today's off-the-shelf technology. And I mentioned that the extruder heater block costs about $110 for the Super Volcano nozzle. You can buy a small heater block for about $1, but if you want to print 10 times faster with a larger one, the Super Volcano, it will cost you $110. So there's a big case for making that, open sourcing that and making that ourselves with basic machining and basic operations. And we'll show you an example of a simple extruder, William, if you can show us that later, for what are the main design elements of an extruder and how can we scale that. So always scalability is a big part of our work here. So we'll start with going to the 3D printer extruder design manual, and let's start by talking about what a basic extruder is made of. What are the main components of that? When we study the industry standards, what we know works today, and how can we build upon that. So sharing my screen now with the remote crew and the people here so we can follow what I'm showing. So general design features. Let's look at the extruder that we're actually using on our own 3D printer, and it's called the Titan Aero. No, not that one. Components of a 3D printer extruder. So this is the standard that we're using right now. You can get this for $117. It's not cheap. When you build them yourself, you can do much better. Then therefore the question becomes, well, what exactly is one? Can you understand one enough that it's a simple task to do? And yes, you can if you know what's going on. So let's look at some of the main components. You've got a stepper motor that's driving a little gear. If you look at the actual parts of an extruder that are broken down in these pictures, the little gear is this item right here. That's the gear that's attached to the shaft, and that's what actually presses. It spins and it pushes a filament forward. So let's actually look at a simple diagram of a 3D printer extruder, since that's what we are using. In a nutshell, in this Titan Aero, you've got the stepper motor that's driving the little drive gear that feeds filament down through the system and through to the nozzle. So you've got a heater block at the bottom, a nozzle at the bottom, you've got a heater element, the red parts going into the block, you've got a thermistor that detects the temperature, it's that little hole back there. In this design, you have to cool, after the heater block, there's a thermal break, which is called a heat break. It's that little part right there. And then you have a heat sink, which is the part under the fan, which rejects the extra heat, because what you do is you keep a very hot section at the hot end, and everything else after that has a sharp gradient towards being cool, so that the melt is only in a heated block area, and very little of that heat travels up into the body. Otherwise you'll be melting the filament before it's ready, and you can get that jammed. You just want it to be hot and molten inside the heater block. The way it works is that the solid filament, and why you need the heat, the cooling, the solid filament acts like a plunger. It pushes the filament below it through to the nozzle, and for which reason the tolerances there have to be relatively decent. Like, you cannot have a big gap where the filament is pushing down on a plastic, or it would like leak around it. Think of a syringe. A syringe has a rubber washer where all the liquid is coming out the desired end, not backwashing through around the washer. And here that washer is your filament. Your filament is doing the pushing. It's like a piston, and you want that to be relatively tight, and for which reason these are somewhat precise devices, and you can get away with not having that tightness there, but at that point you'd only perhaps be able to print very slowly. You want to have the ability to push, nothing's leaking out, and you're pushing with large force. If you have large filaments or you want to go at fast rates, you want the push and no leakage around the filament. So when you get to performance, things in there have to be relatively precise. So let's look at another image of an extruder, just a basic, what is it? Simple diagram. Images, diagram of a 3D printer extruder. So here's a decent one. Let's just take a look at this one for what I just described. Okay, that diagram there is kind of small. Let me go back up. Open image in new tab. Let's just expand this and just take a look at this picture. So it's a simple diagram. You've got the stepper motor. In this case here, what you have is a gear down extruder, and that's actually what happens within the E3D, the Titan Aero. E3D Titan Aero is this one. That's what we're using right now in our printers. So you've got a small gear driving a larger gear, which then feeds the filament. So you've got gear reduction. So you want to push with as much force as you can. The gear designs are necessary if you're working with 3mm and up. If you're using 1.75mm filament, you don't need a gear down from the stepper motor typically. And typically here we're using NEMA 17 motors. So the filament goes down, it gets pushed, and what you see there is what is also found in other machines, such as the wire feed of a welder. So if we open source the design of a generic 3D printer extruder, then we also get into applications like wire feeds for welders, or perhaps wire feeds for mixing in alloying wire into your induction furnace. So anywhere you have to have a feed of some kind of a wire, large or small, this kind of mechanism is quite relevant. So you've got the wire feeding down, you've got a heater element, and then the nozzle and a thermistor, because you need to detect what temperature you're at. You have to know what to set it to. Your software takes care of that, but you have to have feedback to know what temperature you're at. So that's the generic design of an extruder. And then we talk about, there's two main types of extruders. One is direct versus Bowden. So this is the generic diagram here of direct drive versus Bowden drive. In direct drive, you've got the gears going directly into the heater block and nozzle, whereas in the Bowden style, you've got the wire feed that's separated from the heater block on your gantry. So the wire feed, the filament feed, can be mounted anywhere on the printer, farther away from the nozzle. Now you can guess that may be limited. It's got advantages and disadvantages. The advantage of the Bowden setup is then that the tool head becomes very light. You just have to carry the nozzle, pretty much, the heater block and nozzle. You don't have to carry the relatively heavier stepper motor and all the other drive components. Therefore, you're able to achieve much higher speeds, or not necessarily that you're able to achieve higher speeds, but you have less inertial effects, meaning you've got more stable prints So there's less shaking as you reverse direction, so you can go much faster. If you have that entire extruder on a gantry like we do, your frame has to be stiffer to accommodate all of that. But the advantage of the direct drive is that you have a very short path between the feed and the nozzle. What that means that, for example, with rubber filaments, you can do well. Because if you think about the remote Bowden extruder setup, if you're pushing against the rubber filament, that thing's going to crinkle up on you. It does have a guide tube, but you're very much limited to what you can do with rubber in the setup of a Bowden extruder, especially in a 1.75 millimeter. It's going to be like think of pushing a spaghetti with a drive, it will crinkle up if it's not stiff. So rubber performance on Bowden extruders is very limited. So that's the concept of the direct versus indirect drive extruders versus Bowden style extruders. You can also get into extruders that work directly from pellets or trash. Here's one. This is by Sam Smith. He's been here. We're collaborating on this. But here's Sam Smith. You can look at the link. But he's printing his setup right there. Matthew?
Question about the thing about extruding trash, because my understanding was that you have different plastics with different melting points and different material properties, and so it seems like you have to at least select your trash very carefully. Is that true?
Yes, absolutely. If you want to do generic brute force printing with a large nozzle, you're throwing everything in there, you're going to get a mix of uncontrollable qualities, which may be acceptable for a thing like outdoor exterior plastic lumber, which doesn't have to have a lot of precision or whatever. But typically, if you want any engineered control, you want to separate your trash, and more than that, even know what kind of plastic that is. There's many types of ABS or PLA blends. When you think about 3D printing filaments, the material science there, you can have a blend of anything with anything, and you have to know its properties if you're going to have controllable results. Here, for example, Sam is printing directly with polypropylene, I believe. So he had polypropylene that he shredded up and put into the system. But if you want engineered quality and controlled results, you have to know exactly what you have in there, because you don't want your filament to have one property at the beginning and completely different properties at the end of that filament, because you're just going to mess up your prints. So there is the whole material science aspect of that. But the good thing about it is we can experiment a lot with it. Like, for example, if you have polypropylene, which typically is actually quite difficult because it warps a lot, you can mix it, say, with ABS or other blends, and that goes into the science of what mixes with what. There's polar and non-polar and less polar when you talk about the electronic structure of these plastics. Some mix really well, others totally don't like each other. If you have one that's really hard to print with, you can so-called alloy it with another plastic or blend it with other plastics. So there's a whole realm of unexplored science there. And the trick to that would be, well, how do you turn the waste stream, which has got all kinds of random stuff, into usable plastic? I mean, for one, you do have labeled like PET bottles, HDPE milk jugs, and so forth, so you can know some of what you've got to work with. But there's a whole set of tricks there that you have to do. That's the whole production engineering there to get to reliable plastics, and that makes it very difficult. But once you open source that and get proven protocols of how do you do it, then that becomes feasible. But that takes a lot of work, and it's perfect for a crowdsourced effort, because say a plastic in one country may be different from plastic in another country, and so forth. In this trash extruder, when we say trash, you do. I don't want to mislead to say that, oh yeah, just throw anything down there. In cases where you have a blend that has so many different things and it's just acceptable, yes, you can do that, but typically you want to separate things and know more of what you're doing with to get higher quality results. So if you want to get a precision part for a 3D printed calipers, well, you want to know exactly what you've got there. You don't want any imperfections in your print. But if you're printing plastic lumber, you can throw everything in a kitchen sink in there and it may work, depending what you're starting with. So moving on here. So those are the main types of extruders. This is absolutely open source here. There are open source versions of this, but nothing is well defined, well refined. I think Sam is doing the most cutting edge work on this that I've seen, at least. There's a lot of work like this in various countries. Most of it's like partly proprietary and stuff. So once again, we are into the issue of people saying, "Oh yeah, now I'm gonna make millions, and I'm gonna hide this because this is too good." That's a typical issue with open source. Once you get something that actually works, maybe 99.9% of the people disappear, and that's one of the challenges of the collaborative literacy in our world today. Okay, so moving on to more topics here. So let's talk about designing the optimal plastic extruder. So we'll go to a page, and this is something like when we talk about an optimized plastic extruder, that means something that can handle both regular plastic and rubber. I don't see any reasons why you cannot optimize for both in one. So here's what I've drawn up so far in terms of what optimization would look like, and it might look a little different than standard ones. So design rationale. So first of all, if you want really good feed on your filament, you want to have two drive gears, one from each side. If you're driving from one side, typically what happens is you drive on one side and the other one is an idler that does not spin, or it's not actively driven. If you want the higher, this is now for larger, faster, better extruders. You want to first of all start by driving from both sides. Now maybe you even want to do a second set of drive gears to get double that drive force there. Because the thing is, because plastic is soft, it will wear out. You can only push it so hard with a set of teeth before you actually wear it out. So for optimization, you definitely want to start with double-sided drive. And I'm saying this with respect to, okay, how do we take, because for example, we've built one here. Here's an extruder that we built for $5. How do we get this to optimal performance? So start with dual drive. Now, the critical aspect of an extruder, and so let me get into the distance between the drive and the heater block. You want that distance to be absolutely the shortest possible. So if you're driving, for example, rubber filaments, they do not have a chance to kink up and bind up before they get out the heater block. So here you have, what we have here is right above the drive gears, you have, it goes immediately into the heat sink. And in fact, it's kind of like, it's got this upward metal part where it's right after it's driven, it enters the cooling block and gets constrained, so it doesn't have any chance to wobble. You need the heat sink, so there's our heat sink right after the drive gear. Then after that, you've got the heater block. And the goal there is you are absolutely minimizing as much as possible, but with a caveat that if you make that part, this heatsink part there, too thin, you may not get enough heat rejection to cool this off. You might the heater block might overpower you. So this gets into thermal design. How thick does that part have to provide enough cooling? And what you have here is conduction to this other part of the heatsink, where you've got fans blowing on it, like we have one fan on the current extruder blowing on the heatsink. But here I drew that on the side. So why am I drawing this on the side? One critical aspect here is maintenance. I want to leave the front entirely open so that if there is any jam, which will happen from time to time, and hopefully once a year, not like once a day, then you can maintain it, you can open it up, you can pull out the filament, and access to that. Because right now, for example, if you get a bad jam on our extruder, the E3D, you have to take off the fan, you have to take off the heat sink, and the whole thing then falls apart, and you have to put it back together.
And that extruder takes less than a minute.
And that one, so like this one here, has got an open, the one we did, has got an open face. But that's absolutely unacceptable from an efficiency perspective. Then you're becoming a servant to your technology as opposed to doing with your life what you need. So we want to, by design, you want to open front face design. That's why the heat sinks are towards the side, and those ribs or whatever. This is just a conceptual design, but we're taking, keeping the front open. Okay, second part. So you definitely have to have the fans for cooling. What I did not draw here is a print cooling fan, which would blow under the nozzle, like where the filament comes out. You're cooling the print so that the print stabilizes as soon as the layer of filament is deposited. The way 3D printing works is not that you're attaching a molten piece of plastic to a molten bottom. The idea is that the thermal mass of the actual print is melting and biting into the underlayer. Like with welding, you're not relying on the thing you're welding to be molten because it's metal fusing into metal. It's the heat of the metal that's actually melting the metal below that to attach to it in welding. Same here, same principle. That means that if you stop your print for a day and everything cools off, you can pick right up because it's the new filament that melts and fuses into the layers below. That's how that works. So that's called fused filament deposition. The new filament fuses into your existing print. And that's an important concept to think about because that kind of gets you to understand how you can print various things. Okay, so next feature here is I'm using bolts here. Clamp design. I told you about the clamp design right there for heavy-duty bulldozers, equivalent of Cat D7. And here we're using clamp design for this tiny extruder. Why? Threads are tricky. Threads do not give you as good thermal contact as metal on metal contact.
Have you changed the page because it still looks like the...
I didn't.
Oh, okay.
I'm still here. We've got clamps. The clamps are the little bolts. So what I'm doing here, so there's a heat break. The light red part is a heat break. The heat break is the part that connects the heater block to the cooler. So basically you want the heater block to be hot, and therefore the part that you're connecting to the rest of the system wants to be as thin as possible to have the least conduction. In thermal design, conduction is much stronger than convection or like radiation. Conduction is like if you have metal connected to metal, that conducts fast. If you think about something that's, you know, a hot pot on a stove, it's very hot even though the flame is on the bottom because there's conduction. There's pretty rapid conduction. Conduction is what you're protecting against by using the heat break being as small as possible. Now what's the limit to small? The smaller it is, the more fragile it is, so it has to have enough strength that you can still make it workable. So there's two big points for the clamp design. You're avoiding threads. One issue that you haven't seen it, but I have. Our current extruder has got threads. So one, it's weaker thermal contact because threads aren't like 100% meshed. Parts of the teeth are meshing, and a lot of that is airspace. So the conduction there is not great. So for example, on a heater block, you're trying to heat the filament that's inside that heat break, but you can't do it as efficiently. So in a optimized design, you want the heater block itself to be a clamp-on design. The second aspect of that is that you can arrange the angle of the heater block as you need to, because you need to be at an exact angle because the thing is rectangular. Unless it's spherical, the angle unless it's cylindrically symmetric, the angle matters because then you're either hitting the cooling fans or something else. So you need precise positioning of that angularly. With threads, absolute hit and miss. And I don't know how E3D still gets away with that. Maybe most people don't have that kind of a requirement. Here we have a requirement that we need to position the heater block at a particular angle because there are cooling fans around it and a nozzle, cooling nozzle. So if you don't have it the right geometry, you're going to be hitting your cooling nozzle. So you want to control the angle. That's the second reason for clamping. Yeah. Besides, it's easier. you have wires coming out of the top of the heater block. If you're spinning them, you're hitting the wires. Like when you get close to the full thread on, you're hitting all your wires against the top, so it's messy. Here you just clamp it on, you put the wires out of the way. You don't have to worry about wire management when you're putting on the heater block. Matthew?
Question about the thermal conductivity. Like, if
Yeah.
you have with threads, maybe they're not all connected, but it seems like there may be potentially more surface area involved.
The surface area boils down to no, because when you have a boundary that's like this, that is no more different than a boundary that's like that. The amount of heat that
But
you
I mean,
have transferring.
Consider heat sinks that have these great big fins on them to increase the surface area exposed to the air. I mean, it seems possible to me that the screw might act the same way with the metal on metal. I don't know whether or not it becomes the difference or not.
Right. No, that's a fine point.
And then you do have,
But-
have gaps between threads, depending on machining tolerances. There's little gaps.
You do have gaps, but theoretically, if you got so precise of machining, can you get, if you have no gaps, would it be better to have a contact area like that than this? And I think it's really about, so you're talking about heat traveling this way. So let's look at the limits. The ideal thing is when there is no boundary there and you're getting all the heat to it. But so my claim would be, if you have a boundary like this versus a boundary like that, I'm not seeing a difference between the conductivity. It's one of those things of the sine theta thing, the angle, where
I mean, if there's no gaps, then yeah, either case ought to be equivalent.
right.
But I'd wonder whether or not clamping on is a perfect meshing either.
Well,
Depends on the
I think it's much closer than threads, and so we're hand waving here. We don't have like precise data to show it, but you can, at the end of the day, simply take thermal measurements. Like you turn on the heater and you measure the point at which you are extruding good plastic. So you can do that. You can do an experiment. You're taking the exact same system. One is threaded, one is clamped, and you're simply taking data. How long does it take you to heat up? And that's a great experiment for someone here to do. You can do that if once we get this all designed. But that's the kind of data we'd have to take, because maybe there's another effect here that says it absolutely doesn't matter. But the first principle analysis of this says it does, because there's a lot of airspace in threads.
You can also do different threads. You can use Acme threads, which are more squared than the pointing one, depending on what you want to do.
Yeah,
So there's
yeah,
also
so-
that variation.
Yeah, there could be a lot of things. But from the first principles, I would start with this. And why? Why also? It's a third reason for doing this. It's easier to drill a hole than to thread a hole, right? So the machining requirement here is much less. All you have to do there is just like with our split shaft couplers, you have to slit that block, either partial or a whole split. I would do a clamshell. The clamshell is a universal concept, and it's actually coming through as it's becoming clear to me how universal that concept is. But we use that for the axes, because then you can get into disassembly or managing the components inside to have more flexibility, where otherwise the machining requirements or how you put the bearings inside, like that becomes hard. So clamping is good, and we've seen it with a universal axis, with tractor drive, and now with 3D printer extruders. So you're seeing how this kind of the concepts, the underlying concepts, there's only so many of them, but there are good design principles that you can follow to get robust design. So, yep.
With the clamshell, how does the nozzle attach to the heater block?
Okay, details. I'll talk about the scalability of these nozzles, because there are very important details there. Because for one thing, the way these systems work, in order not to create leaks, the nozzle itself, and I'm going to draw that detail right in there right now. So the nozzle itself touches, so there's a part of the nozzle there that's screwed in that touches against the heat break. They're actually screwed to each other, so there is absolutely no leak between them. If you left a gap and there were threads, then plastic would leak out the gap. It does exactly that. If you don't tighten the nozzle against the heat break, you have leaks and your prints get messed up. You eventually get a whole glob. There was like a classic, I should find this, on the OSC Workshop's Facebook page. I showed a picture of what happens when you get a leak out of that. In one case, it was the funkiest thing I've seen. The entire extruder got swallowed up in plastic. There was a little leak, it kind of kept leaking up. The whole thing got encased in plastic. I should show you that for what happens when you don't have that. So let's see, Open Source Ecology Workshops. What is that? Did anyone see that on OSC Workshops? I don't know if I can find it. So search this group, like a extruder failure, maybe. But just to show you, that's the kind of features you have to pay attention to in this system. Like the threads leak, absolutely. Clamping will not leak, so you remove the requirement of butting up the two against each other. So that's another reason why this design can be potentially better. So if you're clamping, the thing on top and the thing on the bottom, they have to have the same diameter. But if they do, when you clamp upon them with a straight split hole, can't find it here, we'll maybe add that to the system here later. You remove the requirement of butting up the nozzle against the heat break exactly, which is a tricky process. I mean, E3D has instructions for doing that. I actually emailed them and say, hey guys, you can never get the angle proper with the way you've got this design. And they said, yeah, it doesn't matter. For a lot of people it doesn't matter if they don't have tighter requirements on the geometry. For us it does matter. With the current nozzle on an extruder, which I haven't really shown the extruders how we have it, but we have a nozzle that's like right next, the fan nozzle for the print cooling fan, that's pretty much right next to the extruder nozzle, which means that if the heater block is turned towards that nozzle, it interferes, so we can't do it. Let's continue. So we kind of talked a little bit. Let's see, here's just another configuration. I was thinking, okay, where are we going to put the fans so that we can still cool the system? And printing belts on a small area, you can just curl up your belt on a print bed, so you can get like a 2-meter belt on an 8-inch by 8-inch bed, mixing metric and imperial here. But that's the case for rubber extruders. Optimized. This deal here is optimized for rubber. The shortest possible path between the drive and the heater part. So I'm including the clamp on both at the heatsink area and at the heater block area, which means that the component there is not a threaded long tube. It could be just a tube, which is much easier. You don't have to worry about first threading that tube. So absolute simplicity. This is the next generation. This is going to be universal in a few years, and you've seen it here. I mean, it has to be. When we talk about improving performance, this is such a gap in the community right now. You cannot really print anything large with rubber right now. Yeah, you can print in rubber, and the people who advertise, oh yeah, you can print rubber. Yeah, you can do that, but very slowly. Not in a way that is economically feasible if you talk about actually making real parts.
What thickness are we talking about with the filament?
Here we're starting with 3mm filament, which is off-the-shelf standard. When we design this ourselves and we start extruding our own filament, we probably want to maybe go to 4 or 5. So you have an easier way to print. When the larger the filament, if you have an error in its diameter, percentage-wise, that error will be less as a fraction of the overall width. Therefore, the quality control requirements for producing filament that's larger are much decreased compared to 1.75 filament. So you can get away, once again, this trash printer and what we call shilament. Guess what that is? Crappy filament. You can have crappy filament, OSC shilament brand, and still get perfect prints, because the variation, even if it's there and it's not acceptable for 1.75mm printing, it will be well acceptable for large printing and large parts like plastic lumber.
Are we talking about rubber that we get from like tires and we convert them to this, or we talking about what type of rubber?
Thermoplastic urethane or other thermoplastics are what we're talking about. This is not the same as a lot of the tire rubber, which is from rubber plantations, rubber trees. But some tires are made from thermoplastics. Like I've seen, for example, a lot of snowmobiles have thermoplastic urethane tracks.
Usually that's abbreviated to TPU if anybody wants to look it up.
TPU, TPO, thermoplastic olefins. There's various rubbers that are thermoplastic. That means you can melt them and then remelt them and use them again and again, which is good for the environment. So how do we get this? If we want significant drive, and you notice we're eliminating gear down. So how do we do that? Well, we'd want to use a motor that already has gear down to simplify the actual extruder design, because the current extruder design has a gear down built into it, a 3-to-1 or so, or is it 5-to-1 gear down. But that makes this design here complex, making the design where you have the drive right next to the nozzle not possible. The way currently the way the E3D Titan Aero is set up, which what we use, it has the drive gear like I show here, and then it has the gear down like up there around this hole here, which means you've already moved the point of drive, because the point of drive is going to be around somewhere like up there. So you kind of like doubled the distance to the heater block. Another thing here, this is what I call neckless, like without a neck design. In an E3D, what you have above the heat sink, instead of making this neck here where the filament goes in, we call it the neck. So let's actually label that. Let's call that the necklace, because it's not a separate part. Neckless, without. Necklace design. The neck, that part where the filament gets constrained right after gear drive, it's part of the heater block. In an E3D Titan Aero, there's a separate plastic piece where the filament goes into that before it goes into the heat sink. We're eliminating that, so for another thing, we're eliminating yet another part. The importance of that is you're shortening down the distance. So when E3D had their geared extruder, the drive was somewhere further up. In order to not to crinkle that filament before the heat sink, they have to use that other constraining neck piece, basically a tube that goes into, it constrains it. But it's a small piece, it's like you got to get it in there, it adds to complexity and so forth. So the idea here is start with a direct drive system, meaning what you have, the stepper motor there, is already geared down. You want to use a light stepper motor like an EMA 17. This is, for example, an EMA 17 with a 5-to-1 gear down that you can apply in this system. But we also talked about OSC Wiki 3D printed planetary drive. Let's show this. So let's get a built-in planetary gear down onto a regular NEMA 17 stepper motor. So planetary gear 3D printed let's look at what 3D printed gear downs look like. Uh, 3D printed
Speed reduction.
planetary. There. Look at that. That's an EMA 17 motor. And this right here is feasible for what we are showing here. This is about $30 or $40. This here is a couple of dollars plus an $8 stepper motor.
Is there a breakdown of the inside of the planetary?
Absolutely. Look at there's a link, source with great explanation of planetary gears. So you go there, and it's got the full design, 3D CAD files that you can print right now. Very powerful. We're hoping to get to some of this, but I don't think we really have the time to actually build these. But here you go. The way they, and this is Arduino with a stepper driver, like our ramps. And see how it can spin very slow, very controlled. The tricks there would be make sure you have enough accuracy there. But for gear drive, the accuracy is not that critical. What you have in an extruder is the idea of retraction. That's another concept to consider here. But whenever you're printing and you jump over to another place, you don't want a little strand of filament to keep dragging. You want to suck it back up. So that's retraction. In a motor like this, the only challenge is, do you have enough accuracy to do retraction properly? I don't see why not. You spin it one way and you spin it the other way. It's not like, we may have some difficulties using this for, say, the axis drive. I don't know, haven't tried it. So you'd have to make sure your prints are pretty good in order to be able to retain the accuracy. But you can also think that the way to address the accuracy here is you have this brute force printed, 3D printed gear down, and then you can have, instead of direct drive of a pulley, you can have another gear down where at the end of the day it might actually work out, because a gear down, whenever you have a gear down, that step motion is going to be decreased. So right now we have 10 microns. With a further gear down after this, or maybe if you gear this down enough, so you already have the stepper motor, which we said has 3,200 divisions per revolution. Well, this is getting you even finer motion because it's already gearing that down further. So there's a case to be made that this could actually be more accurate, even though it has maybe a little backlash, meaning the non-meshing. And we covered backlash yesterday. The meshing, the non-perfect, like there's a little space between gears. Even though if it has backlash, if the gear down can compensate for that and actually do better, say it's a 5 or 10-fold gear down, if the backlash got your results twice as bad, but the gear down compensate, you can possibly do actually even better. Experiments to be done. So the idea being, like, if you engineer this or you keep playing with this and refine a system, you're freeing yourself from depending on these, which are much more complex. So moving on, let's talk about scalability. So we covered a bunch about the optimized design. Let's talk about scalability, and then we'll wrap up with how do you design filament makers, which are quite related to this. You're melting plastic, and you're extruding that and pulling that out, so it's just a filament that you roll in a bunch. So let's talk about scalability. We mentioned that you can buy a small heater block for $1, but if that heater block is about 5 times bigger, it's like 2 inches long, it ends up costing $110. So this heater block, they have ones that are that long, that's the super volcano, but it costs quite a bit. So how can we do better with simply stacking 2 of these together? So take 2 volcano nozzles next to each other and stack them, just like this. So there you go, single 40-watt heater block, you're doubling them, tripling. Why don't you keep going? The limit's going to be how much plastic you can melt through that, like the thermal contact area, and then you need more force to push this. But two of them, yeah, you could absolutely do that with the existing Titan Arrow. Just put two blocks on, but there's details of how you would do that. So let's take a look at that. We mentioned, so in the threaded design, these are details for threaded design. If you wanted to take off-the-shelf existing parts that cost a few dollars, double that, so you get under $10 for a $110 value of heating power otherwise. So when you thread them together, so first of all you've got a heater cartridge in there, the purple stuff, and then you've got a thermistor, so you've got a little bit more of wire management. But how would you do that? Well, design detail using standard parts would be you have the existing heat break, you follow that with an M6 threaded through hole thing. Like, you can actually get bolts that have little holes through them. Like this is from McMaster Car. That's a FreeCAD step file imported from McMaster Car. Yeah, that's accessible. So you have an interconnecting M6 threaded through hole piece of threaded rod. You can get those off the shelf, and then you simply connect the next the volcano nozzles look somewhat like that. They thread all the way to the top. So we talked about that leakage issue. In this kind of a design, you're required to butt up everything tight and screw it in tightly. You can't have leaks. So this might get a little challenging, like, because you're going to have to butt that up, these two up against each other. So you have to kind of screw it in through that. Or maybe you can take at the very end of the day, just take the volcano nozzle and screw it in tight so it tightens both this gap and that gap. Tricky. I mean, tricky stuff. So maybe this is like not that easy. You have to get good at it. This is the kind of stuff where working with threads is just hard because threads behave. You know, you've got the threads inside this heater block and inside this threaded compartment. I can't predict what's going to happen here, but theoretically you can do this, and this probably will work if you get it right. But you have to watch out for leaks, like the budding of these where the breaks are. So what about doing this one real super long nozzle? Yes, they exist. You can get one for a few bucks for the super volcano. They're like maybe $10 or so. So yes, you can use and stuff. This is the volcano nozzle. You can use the super volcano nozzle, so you can eliminate that block right there. But this is once again where the next step. See, like right here, we've got the example. We've got the heat break and a super volcano nozzle, which is long and it stretches through about 2 of those heater blocks. So maybe you can do that. And what about this? Yeah, if you keep going further. So in this, so you can kind of think about this. What the deal is. But once again, the control of the angles is going to be like good luck. But the only relevant part for the angle will be the part at the bottom where you want the fan close to it. So maybe you can do it. Or maybe like mount the fans, cooling fans, just farther away. So design that angle dependency out of this. But then you'll get pretty much all your printers will look a little different. They might have the heater blocks. Each of these heater blocks might be at a different angle, which is just visual. It could still work, I guess, but you have to consider ease of cable management. You want it all to be nice and neat so you can manage everything properly. So the next deal on this would be, what I would suggest is do exactly this with clamp blocks. So now you can cut your simple tube to be as long as you want. At the end of that tube, you still need the contact between the long tube and the nozzle. So that's a missing link. You'd still have to get that nozzle tight against that whole tube, which is incompatible because you can't. How do you mix clamping with bolting? Maybe you can thread the very end of that, screw that in. The rest of it is unthreaded. When you slit it, it might just end up that it comes back. Nah, too tricky. So here in a scalable heater block, you are probably left with, you've got a long tube, and into the end of it, you would have to make your nozzle part of that long tube, which I guess that's a little bit of machining there. So
how about tapered nozzle that as it clamps, it bolts it? The tapered side of the nozzle on the inside?
oh yeah, okay. So right.
Like collets.
Right. So, thank you. So, we said that if you have a clamp design here, which I haven't shown any clamp designs here because I was thinking about using off-the-shelf parts because we haven't done any of these other things. So something that anybody can get without having to slit and find these other parts that are easily doable, but nobody is doing that right now, so you can get the parts. So you got a long tube that's straight, it's clamped on. At the very end, you just machine your nozzle to be without threads, period. Done. So that's what you got to do. But that depends on you having to machine that little, or find somewhere, or machine that nozzle that's without threads. All of them come with threads right now. Nobody makes unthreaded heat breaks or nozzles that I know of. Now the other company called J-Head, those guys actually make clamped systems. And there's arguments that J-Head is actually, the technology is going to go towards what J-Head is doing because their nozzles are pretty high performance. I talked to those guys at the Midwest RepRap Festival, nice guys, and we were sharing these thoughts about the perennial issue of threads, and they completely got that. They don't use threads, and they said that's a bad idea. So they have press fit parts. So I think the 3D printing industry is going to go this way for clamp.
Service that later. Yeah.
You don't. So when you do press fit, it's kind of hard to service because once you press fit that in, it's really hard to break it apart because the metal might fuse into itself. So it's kind of not the way to go either. Got to go with the clamped stuff. So I think, personally, I'd say the clamped designs are going to be the future of 3D printing scalable nozzles as we actually get to real printing. Right now, everybody's doing hobby printing. Not a lot of, we could say probably the industrial printing with the existing open source 3D printers out there is less than a hobby style. Definitely a lot of businesses are starting to print real parts. Lulzbot is a great case. You can go to lulzbot.com. They have a lot of case studies of various people from GM to the military using their 3D printers, which is kind of interesting because now Jeff Moe is servicing the military industry. But
At least he's open.
In open source, you have to be use agnostic. You're going to sell your printers. It gets a little controversial there on who we're supporting, but I don't know. People, if you've got employees, that's a requirement. Otherwise, you fire everybody or find new markets.
So remind me what's wrong with threading? It's because you can't control the angle?
And it leaks.
There's three issues. You cannot control the angle.
And the angle of the final angle of the block.
Okay, so you're threading in the heat break, and then you thread in the nozzle, and then you keep it loose, and then you screw in the nozzle, but where it's going to bottom out.
Well, you have to use the block as a jam nut. That's how we did it with Brutish nozzle.
Yeah. When you do it, it's okay if you were not heat tightening later, but there's also heat tightening. When you tighten this up, the other aspect of this is to get it into final position, you need to tighten it under heat. So that's another step you have to take. With a clamp on, I don't believe the heat tightening is a necessary step. But the angle, I can show you on the real printer like where it gets troublesome, but you can't get the angle. So the angle, lower thermal conductivity, and much more difficult fabrication. I mean, I think that's a compelling case.
You have a gap.
You have a gap.
You got your gap in your clamshell. So
Yes,
with
you
these,
do.
I just wondered.
But that's not where the plastic is.
It's on the inside of the
It's on the
tube.
inside of the tube.
Okay.
So you get away from it.
you have
But
a
you
very
are right.
flat
At the
bottom.
very
You
end,
just have a very flat interface there, or a taper.
No, you are right.
Really
There-
good, SAE style
yeah.
taper.
There's still the issue that if you're clamping this on, unless you're pushing this nozzle up against the
Can you
The inner
can you do
tube?
an inner thread on the end of that tube? And the outer thread on the nozzle? Or do we get
Oh yeah, there you go.
string?
Oh yeah, there you go. That's an
And a
answer.
little tap and guide set.
One answer for that, because yes, Aiden's pointing out, and it's a good point, that when you have the slit through that, you have the tube which contains the plastic in there, but at the very end where it goes to the nozzle, you have that slit. So unless that slit is perfect, that it's clamping onto itself as well as the tube inside, you can have a leak. So Aiden's suggesting, why don't we do the long tube, thread the very end of it outside, and have a nozzle that's got a small nozzle that's an inner thread that just tightens on that. So you have the tightening like right there just on a nozzle, and that's it.
Awesome.
So
I think
that's a
works.
good idea.
It's like a funnel.
Yeah.
A funnel. Right.
Yeah, so
No
you're reducing your threading complexity to a small little distance. The difficult part comes when you have very long threads and very long through holes. That's kind of tricky to machine. Like we talked about rest yesterday, something you lay against your piece. If you have something that's like 2 inches long and you're machining that and it's really thin, like at the very end, I mean, how are you going to machine that? You're going to be wobbling that nozzle. So you have to probably, in the machining process, they probably are using some form of rest or stop against which that thing can rotate in order so when you're threading it, like machining that, there's different ways to machine, but there's definitely challenges on the production engineering side for long threads.
I think a couple days ago you mentioned EDM, which is good for cutting small holes and
Yeah.
things.
Yeah, EDM could possibly be done. Now EDM, spark electric discharge machining, is very slow. You're talking about like very slow and expensive. It's good for some heavy duty cutting, but I have a hard time seeing how you're going to make inexpensive nozzles with that. Okay, so multiple blocks. We covered that a little bit. Last thing is open source filament makers. So we can start with, well, 3D printer extruder. Well, let's cover this one real quick. But here, what William did here, this is a basic design that's
Copied from China.
copied from China. And do you think this thing works?
We haven't tested it yet.
Yeah. So we still have to.
There's one detail. It needs a shorter screw. I just put whatever M3 screw I had. It needs a shorter one so it can fully flex around. And also, there's a part that should be in your mailbox that goes right there.
Okay.
Somewhere in your house should be the other part.
So you can make these things like the complexity is. So here we have the heater block. So if you want to make a low, like let's start with a low-cost extruder, not filament maker, but extruder. Heater block, heat sink. And where do you put the fan? Like
The fan can go on the outside.
So
it actually attaches to this screw, and it just swings back. And for this, out of all the extruders I've ever seen, it's the most reliable. It's like in 3 years, it jammed like twice, and when it jams, it's a 5-minute process.
Yeah. Can I show that to the
It's less than 1
people
minute.
outside? So this is an example of a homemade extruder. Heater block. It houses a little heater element, your nozzle, your heat break, heat sink. There's a gear that's missing, but this is the filament feed. The filament goes in there and gets pushed through. So this is on a wiki under simple extruder. Now, let's talk about filament making extruders. So now the device that gets you the filament to 3D print with. Because one of the ideas is that filament is 20 bucks a kilo, 10 bucks a pound. You're going to make a chair or a piece of plastic lumber, it would be rather expensive. It wouldn't be affordable. So you want to get into making your own filament from scrap, which then costs about 10 or 20 cents a pound, as opposed to $10 a pound. So talking about a factor of 100 cost decrease on your access to filament. So let's go to Precious Plastic is a nice project out there that does that. They have a design that, start with a shredder. So a shredder, this is an open source shredder. You can look at Precious Plastic. What does the filament maker look like? So let's go to Lyman Filament Extruder on the wiki. So this is what we have built and we have used successfully. So you can go Lyman Filament Extruder. That's Hugh Lyman. We visit them. He's out in Washington State.
Can we change that to the screen mode?
Yeah. So back to screen. Lyman filament maker. So that's the CAD and FreeCAD. This is the Lyman we built in the bottom, and this is what we had going on. So you've got the hopper. It's a wall-mounted system. It's actually in a workshop. You put pellets in there, and you're extruding filament. And we've got plus minus 0.1 millimeter out of the system. You've got a spooling system where, as you're making the filament, there's a roll that rolls it up, and it's activated. The way it works is just the filament drips down, and it's on off like when it's. This is the spooler, but the way this spooler works, it turns on and off periodically. So this is the actual spool we made. But you see that there's an on-off switch. That switch there, like when the filament just dribbles down, it falls down and it activates that switch to activate the spooler. And this is like, we got to improve that. I mean, these rubber bands and stuff. It needs a little refinement. But all the systems are there to make that work. And this is what we got. Looks beautiful. This is from pellets. This is not from trash. Pellets are $1 a pound in bulk, or down to 50 cents a pound. 50 cents to $1 a pound if you buy a ton. If you buy a small quantity, they're like $4 a pound on eBay. So at $4 on eBay, you know, you're getting close to the $10. It's about half the $10 value. But if you get bulk and you actually start doing this seriously, yeah, there's 10x lower cost from pellets and 100x lower cost from trash. This is great, but we don't stop there. We said, okay, Hugh, let's simplify this. That's a little too much there. So how do we do the absolute simplest version of that? This is the next iteration. I call it the simple 3D printer filament maker extruder. Let's take a look at that. This is on FreeCAD. Clearly you would go to the link in the Facebook page, 2018 simplified version. The CAD, where's the CAD? There's the CAD. You can download it. Let me download it. What happened there? I'm going to download this file and show you in 3D. But I said, okay, there's our filament maker. Still too complicated. Let's make it more simple. So this is the simplified filament extruder, and using now much more standard off-the-shelf parts. Hugh is printing that casing and putting all the components in there. But how do you do it with like 2x4s and while retaining heat safety and all that? So let's take a look at this one. Just stripping down any extraneous details like the 3D printed parts. So instead of doing what Hugh's done there, I'm doing this. So there's like a 2x4 on the back, your power supply is on the back. If you open that up, how do I hide that? It's not hiding on me. Well, basically I attached the controller like right on the side. There's now we were starting to see the insides of it. But basically the space, this is 2x4s or 2x6s there. You got a hopper here, so you fill this whole thing, and there's an extruder, basically a drill bit right there. In this case, there's a, let me hide that. There it is. So you've got a coupler, you've got your auger, which is a 1-inch drill bit. I would make this into a 1-inch system. Hugh does this with a 1/2-inch bit. The precious plastic guys use a 1-inch bit. Why 1 inch? So you can just throw more nasty stuff in there with more resilience. So you want it larger. Here with the Lyman filament maker, you've got a single heat band. You can make multiple heat bands, say for a 1-inch extruder like this. But the compartment in there carries a few pounds of pellets. You throw that in there. It's wall mounted, the controller is next to it. There's a metal plate, so this gets hot right here. So you got a flange, and then you've got a piece of metal. So metal against wood, but by here it's getting, you know, if it gets too hot we can put fans on this. But this is, detail. So you've got the metal flange, underneath it put an insulating piece of metal, and then on the other side, so essentially there's no contact between the hot part and this metal here. So this metal should be lukewarm. Put an insulator under this flange here, and there is no contact here because there's a big hole. Huh?
Just putting a sheet of that welding blanket there.
You can put, like, yeah, welding blanket, for example, is a good insulator. It's a high temperature thing. That thing, that's like thousands Celsius or something. There's heater, called welding blanket, and I think it's made from, what, carbon fiber, is it?
Yeah.
It's a carbon fiber metal welding blanket. You can use like a ceramic thing down there, maybe standoffs, ceramic standoffs, but this is the hot part. You're talking about 200 C. 200 C and wood do not mix. Pyrolysis begins around 100 C or lower, like 80 C. You start breaking wood apart, and this is 200 C. So, but I like the wood idea. It's like this is just simple metal plate and wood, and there you go. Now for the motor there, that's the motor that we've used like in the pictures. But look at this. I mean, that is super simple. You can build that in a few days from scratch. The controller is here. So what do you have in a controller? You have the same solid state relay. You have a knob for selecting temperatures. So there's a temperature controller. So this is essentially your thermal probe. So like the thermistors in our printer system. You've got an on-off switch. You've got a power supply in the back. This is 12 DC for off-the-shelf heater blocks. But we are learning about what we're doing in the shop right now. We have built the heat beds, which are nichrome embedded in fiberglass sleeve. So get rid of the power supply. Use 120 AC. Use the universal controller. So now that I'm thinking about it, I haven't come to this since months, but now I would just put the OSC universal controller on this and forget about all this novelty here. You can have the capacity to turn on a solid state relay and 120 AC. I would get rid of this, which is a whole bunch of different things arranged differently. Use the existing 3D printer controller, and then you have an LCD screen so you can be more precise in what you're doing there. So that will be the next step on this. Awesome.
So I think, do you think the hardest part will be to make the heating element on the bottom?
No, it's
actually
one of the
buy it.
easiest parts. You can buy an off-the-shelf, like a $5 heater element, or you can make it. When you buy it off the shelf, you're limited to like whatever, it's 100 watts. With a nichrome wire, you can make it 500 watts or whatever. But here, the hardest part, I would say, is the nozzle, where you have a little through hole, like 1 millimeter or so. I think in Hugh's system, he's using a larger than the filament hole size. Like he might be using like 3 or 4 millimeters for 3 millimeter filament, because as the molten filament drops down, it thins down a little bit. And there's two ways to think about it. You can have the hole that's smaller or larger depending how you're pulling it. So little details there. But to me, the hardest thing is you have a nozzle with a little hole through it. So you either have to buy that somewhere, or possibly even use like the 3D printer nozzles that you drill out. The largest they make is 1.2 millimeters. I guess you can drill that out to 3 millimeters, and it could work. So maybe instead of that brass plug, you're using another fitting that's reduced down to where you can screw in the 6 millimeter 3D printer nozzle. That might be an interesting thing to do, because otherwise you have to drill something from scratch, whereas if you already have that nozzle, you can remount that hole. It's self-guiding. It will be very straight. So that might be an advantage of doing that. So that's it.
Multiple nozzles for different thickness.
And then you can screw in the different nozzles for different filaments. So that's the basics of the 3D printer filament maker. What are the critical things? You're controlling a heat element. You're augering the pellets that go in there. And before that, you want to shred, so you're working from trash. And the shredder, let's just go check out the shredder. But what you need to do for the shredder is look at precious plastic and replicate that. So that's doable, but the current design of the shredder, the mission there is that it wears out too fast. It's got 1/4-inch blades. I would do this system and then cut out 1/2-inch blades that, when scaled, get you to your rock crushers and things. But do a little bigger than this. What people found was these blades on this tend to wear out too fast. They're just 1/4-inch thick. When you're talking about even grinding plastic, you've got rubbing and stuff like that. So you want to harden that. So maybe after you cut if you cut with a torch, there's already some heat hardening happening because a flame hardens steel that it cuts, even if you're doing mild steel. So not laser cutting, but torch cutting with a carbon-containing oxyfuel gas, so like oxyacetylene. The carbon that comes from the flame actually hardens the steel itself. So shredders, precious plastic, if you haven't heard about it, Google that. There's great videos on there for how to build all these machines and things like that. In the extruder, some people call for a breaker plate. So in the more advanced versions, you would have at the very end of the tube, you would have a breaker plate, so a little plate with holes in it so that it balances out the pressure and maybe blocks impurities if there are impurities in your plastic. But that would go inside, like right past the auger bit. The auger bit reaches to within, like, just a few millimeters or 1/2 inch of the nozzle, so you're just augering and just pushing it down. And gravity helps. You have to use less force in terms of augering here. So I think the wall-mounted design is decent for doing that, as opposed to horizontal, where you won't get gravity assisting you. Here it's like you're going to have a more uniform flow, because in the horizontal system, gravity draws things down. So this is easier at the DIY level.
Does room temperature affect once the
It would.
filament is coming out, or do you have to have
Yeah.
cool it down at a particular
It
time?
does. Because we have in our system, you have basically like this thing dribbling down from your wall, like a meter of this filament. Depending on how hot the room is, if you're in the Arctic and it's it's near freezing, I mean, obviously that's going to get you different results. So you want to control the temperatures of that.
You want to cool it
somehow
quickly though, don't you? Because you'll get
Because you're going to be now blowing it.
So the interesting thing about the Lyman filament maker is we're doing no fans,
Wow.
no cooling. So what happens is you extrude the gob, kind of thins out a little bit, but
It's just
because
of
gravity,
the steady rate of pull.
pull,
Yeah.
it's just gravity that's pulling it. So it's
So it reaches a dynamic equilibrium and it
It
not
does.
subject to so many anomalies.
yeah. So Hugh said he was in his videos. He's showing plus minus 0.05 millimeter, and when you look at the picture, I mean, you can't see any differences in thickness. It's actually pretty impressive. To review that, this filament, I mean, looks pretty good to me. We can bring it down if you want to actually test it. I've never used it because I'm too proud of the first roll of open source filament. Yeah,
Our students
it's
will-
ABS. Okay, so last topic. Do we have anything else here?
Solid-state readings.
Okay, so getting back to extruders, one important part about extruders is the retraction, because that's what's going to get you perfect. Let's talk about retraction. Maybe wrap up. That's one good thing you have to think about, because this video here shows you the different results when. Okay, that let's put out of it. But let's refresh that page. But this cover page here shows you that's when you don't have enough retraction and you're skipping between one post and the other. You have a little piece of filament that's just dangling, making this complete thing that shouldn't be there. That's perfect retraction. You retract just a little bit so the filament pulls away and you're clear to jump to the next place. If you have too much retraction, you're actually pulling enough filament that you're not able to extrude enough,
When you start printing again.
when you start printing again, and then you get very weak parts. So do this test. That'll be like your ultimate arbiter of your retraction settings. In the Cura, the interface, you select the length of retraction and speed of retraction. And that's some of the settings that when you're doing production engineering and you're open sourcing that goes into your initialization file that you save and give to other people to say, okay, now I've figured how to print this exactly. These are all the settings. This will be one of the settings. Because, you know, depending on your many factors, what filament you're working with, all the filaments will behave slightly differently. So you want to optimize this for every filament and save that settings file so you can do that. You don't have to do the figuring out the next time. So I think I'll wrap up with that and maybe take any questions. So here in this session you got some insights into what the optimized, the theory, what an optimized filament extruder for a 3D printer would look like. Let me quit the screen sharing.
How many size of filament it handles?
Which
Do you have extruder which handles different size of filament?
the extruder that we have can actually run with 1.75. There's basically two things you can get off the shelf, 1.75 and 3 millimeter. The Titan Aero can actually run with 1.75 when you have the 3 millimeter system. It'll be a little worse than the dedicated. You can print. The adjustment happens within Cura. You tell Cura what thickness filament you have. So if you made your own filament and it's 2.5 millimeters, you put that into Cura and then it extrudes it according to that speed. But you cannot do 4 millimeter filament.
There's room in the extruder.
There's room in the extruder for it. But you want to match, like I talked about, leakage and the plunger idea. So you want to be as close to the physical system as possible. So for example, 4 millimeter will not work. The neck and the holes in there don't let you put something bigger than 3 millimeters in. Now when you design your own, you can make a larger one that does handle. Yeah. The other thing about extruders is there are filament with sensors. So you can add a sensor that detects the filament width as it changes throughout. So say you make crappy filament, you add that, and that's a feature already available within Marlin. So you can add this other component to your extruder, which then adjusts in real time for the thickness of your filament. So in principle, when this is all worked out, you can make any kind of crappy irregular filament and get really good prints. Really good to a limit. Yeah, I mean, people pay a lot of attention. Like for example, I know Prusa printers, they make their own filament, very, very tight tolerances. I think they do like plus minus 0.01 millimeter. But they have a 1.75 millimeter system, hobbyists, for people who want really good looking prints. That's somewhat of a different application because we don't care that that print is absolutely perfect if you're talking about building construction materials.
Yeah, you could build a house.
Yeah.
The extruder is big, right?
Right. So that would be paste. So like that would be concrete paste extruders. Yeah, you can build houses with 3D printers too. That's a little different. That's the syringe based, or you're pumping a lot of. Yeah, you're pumping. So actually, let's show that as a what's the benchtop example look like. There's this is a good one. The one to be for us to do is the one from Penn State University. This is back to the screen again. This is what we want to do. This is fully open source. So that's your syringe, and it's feeding into a small auger. So instead of a filament of plastic, this is a modular setup that allows you to do that. That's awesome. It's modular, so you have this device driven by a stepper motor. You're limited to certain size prints because you can only hold so much paste in there. But supersize it, gear it down, and you can print large objects. I'd love to print my own flameware. So cooking pots, that you then bake in a kiln that we did with our open source heater element. So there are very practical applications of this. You can make ceramic offsets for our filament maker, custom 3D printed ceramic offsets. In that case, you'd want to bake them. Here, the process maybe you can do maybe raw pastes, but if you want ceramic that's bonded like brick, like ceramics, you need to fire it. So say we can 3D print our own, like the toilet for example, or sink for our open source biodigester. There you go. Supersize this nozzle, use ceramic paste, like porcelain. Does porcelain come in powder, like clay? I guess it does, because how do they do it? So yeah, porcelain, clay, flameware, ceramic offsets. I think there's a great use case for this. Once again, a little bit of development.
Clogging. How do you prevent the nozzle from getting clogged?
Design as modular as possible, so you might have a system here where you might have, for example, another syringe that does your water purge at the end, and you can perhaps automate that. But otherwise you just have to clean that out after you're using this. So you print it. If you keep using it, you just keep refilling it. But if you let it dry, you want to clean it. So that's the challenge here. You don't just leave it like 3D printing filament, which just solidifies. Here you have to have an extra measure for cleaning, or have a self-cleaning system. For example, a self-cleaning system would be a system where the extruder is geared down so hard that you can break through the clog upon startup, or have some kind of a wash-through system. So that's where the scalability to solid parts and the ability to modify this is useful, because then you have absolute control of what you can do with this, as opposed to maybe some limited applications. But this Penn State work, I just recently found out about. I didn't even know about this. But it appears to be absolutely open source. This guy, this is what he's printing with this kind of stuff, like past work, I guess. He's doing 3D printing. This is clay.
Nice.
Man, that looks pretty.
You can
Pretty
make a business
impressive.
out of that, art, sell art.
You can do a lot with this. I'm not sure how he's using this, how this metal object, I don't know if it's metal, but you can do metal embedded pastes where you center that at the end, so you bake it at the end, and the paste part evaporates and you're left with a 100% metal object. So that is very powerful. That would require some development. There's companies doing that. The open source version of that would be very welcome. So I think I'll end with that. Any other questions? So in this session you've gotten the insights on a basic theory for how you design an extruder. So the challenge for the world is to design the optimized extruder, simply because of the fact that an optimal extruder today does not exist. You cannot print rubber fast right now. Not at 3 millimeters. There is one that's optimized for 1.75 millimeter. It's called flexion extruder. However, 1.75 millimeters is limited by the fact that it's smaller than 1.75. You can only go so fast with it. So the challenge to the world is, let's bring forth the optimized 3D printer at low cost to the world, built with fully open source tool chains. Now for the cordless drill challenge, not sure if we're going to get there. The production engineering for building a 3D printed cordless drill will include the filament maker. So that's going to be part of it. But I'm not sure, I don't think we're going to be hitting. No, we have to. We actually somewhat have to, because if we're going to do optimized printing of 3D printed cordless drills, I believe we will have to insert the design of the optimized extruder into the design challenge. If we're going to talk about meeting or exceeding industry standards, we need the best there is. So I think the optimized extruder will likely be. Now the challenge is not written yet, but now that I'm thinking about it, it does make sense for this optimized extruder to be there. And why? It goes back to our mission. which is collaborative design for a transparent and inclusive economy of abundance. The inclusive part is that the cost has to be low for everybody to be able to access this. So by definition of our vision statement, I believe we have to put in the optimized extruder into the challenge. Because we're talking about making some impact with it. Therefore, we will have to put in the resources to make that happen. So I'll wrap up at that. That's a definite great project for next year. It will be getting kicked off September 2020. That will be the challenge kickoff date as it currently stands. Any other questions? Okay, so let's get back to action in the workshop. So thanks everybody, and we'll continue again at 2 p.m. on the video sessions. Bye-bye.